Before we can look at oxidation numbers, we need to very quickly recap what redox is in terms of oxidation and reduction. So if you remember from key stage 4, historically oxygen was thought of as a gain of oxygen and reduction as a loss of oxygen. But then we moved on to the idea of oil rig, where oxidation would be the loss of electrons, so that's the oil. Oxidation is loss of electrons, and reduction is gain of electrons in a reaction. So when we move on to oxidation numbers, we need to think of an oxidation number as the number that's representing the number of electrons that an atom uses to bond with another element within a compound. So in terms of oxidation and reduction, any increase in oxidation number is classed as oxidation. Any decrease in oxidation number will be classed as reduction. There are, of course, as always, some rules when it comes to assigning oxidation numbers. Very basically, an uncombined element has an oxidation number of 0. So if we had an element all by itself, let's say sodium, Na, then its oxidation number would equal 0. Likewise, elements that are bonded to identical atoms, for example O2, H2, etc., they are essentially just elements, so they also have an oxidation number of 0. If we have a simple ion, so let's say an Na+, then its oxidation number is equal to the charge on the ion. So if we have Na+, then that has an oxidation number of +1. If we have a compound, then the sum of the individual oxidation numbers of the elements has to be equal to the overall charge of the compound. So if it's a compound that has no overall charge, then the sum of all the oxidation numbers must equal 0. But if it has a charge, then the sum must equal that charge. And we can see that in the complex ion here of NH4+. So that tells us that overall there is a +1 oxidation number left over. So the totals of positives and negatives must end up as +1 overall. And the final rule is that the most electronegative element in a compound always has a negative oxidation number. So if you've got one more electronegative, that will be negative, whereas the other one may be positive. And here's a summary of those rules. There are a few exceptions to those rules, and they can be seen there. So elements in compounds, if it's O, then it's always -2, except for if it's in a peroxide. Okay, for example, H2O2, hydrogen peroxide, then oxygen's oxidation state is actually -1 rather than -2. So that is an exception to the rule. Fluorine is always -1. Hydrogen is +1, except for in metal hydrides, okay, where it has an oxidation state of -1. So we always think of hydrogen as being H+, +1, but actually if it's in a metal hydride, then it will have an oxidation state of -1. Group 1 metals are almost always +1 oxidation number, and group 2 metals are almost always +2. We often see oxidation numbers represented in Roman numerals when compounds are written down. And that helps us distinguish between compounds of the same element with different oxidation states. Iron is the prime example that we use quite a lot. So here we've got FeCl2, and that is iron 2 chloride. So the iron has an oxidation number of 2, so 2+, and here it has an oxidation state of 3+ because it's iron 3. So the Roman numerals actually help us in determining the oxidation number. So let's have a look at some worked examples. So we'll go through and work out the oxidation numbers of the constituent elements in CaO. Now we can see that it's a compound and it has no overall charge. There's no charge associated to that calcium oxide there, CaO. So we know overall it must have an oxidation number of 0. So let's break it down into its constituent parts. We know that oxygen, it's not in a peroxide, so oxygen has an oxidation number of -2. So if the oxygen is a -2, we could use algebra to help us sort this out, but it's quite straightforward. If the oxygen has a -2, then the calcium must be a +2, so that overall the oxidation state is 0. As discussed earlier, we can also determine the oxidation number based on its systematic name or its formula. So here we've got iron 3 nitrate. It tells us that it's iron 3, so therefore the Fe must have an oxidation number of +3. So there's the +3 for the iron. And we know that NO3, the complex iron nitrate, has a 1- or a -1 oxidation number. So if we've got +3 and -1, we obviously need 3 times this -1. That then gives us a ratio of 1:3 for Fe to NO3. So we can determine the formula as being Fe NO3 brackets 3, because we need 3 lots of that NO3. As we know from key stage 4, redox reactions don't happen on their own. They're always simultaneous oxidation and reduction reactions. So if there's oxidation, there is also reduction taking place. And we can see that in the example of reacting sodium with hydrochloric acid. Let's look at how the oxidation number of sodium changes in this reaction. Here on the left, it's the element, so therefore its oxidation number must be 0. Has to be 0 because it's an element. Whereas the oxidation number of the hydrogen, because we're looking at the reaction with the acid, we know that chlorine is -1, so therefore the H is a +1. Look what happens to these numbers when we move to the products on the right hand side. Now that the sodium is attached to the chlorine, its oxidation number has increased from 0 to +1 because it's attached to the chlorine, which has a -1, therefore the sodium must have a +1. And if we look again at the oxidation number of the hydrogen, it started off as +1 here, and because it's in its elemental state here, then it has to have an oxidation number of 0. So it's decreased from +1 to 0. So that tells us that the sodium is oxidized because its oxidation number has increased, and the hydrogen is reduced because its oxidation number has decreased. Sometimes you're asked what an oxidizing agent is, or a reducing agent in a particular experiment. So as long as you can remember that oxidizing agents are the substances that cause oxidation of other species. Okay, so an oxidizing agent is often the one that is reduced. And reducing agents cause reduction of other species, so they are the ones that are usually oxidized in a reaction. So let's take a look at this worked example here. So we're looking at sodium reacting with chlorine to make sodium chloride. So let's identify the reducing and oxidizing agents in this reaction. Before we can start, we have to identify whether things are being oxidized or reduced. So here we can see the sodium is going from an oxidation number of 0 to an oxidation number of +1. So that's the sodium. The chlorine is also going from an oxidation number of 0, but this time if the sodium is +1, the chlorine must be -1. So the sodium is increasing in oxidation number, so therefore it's oxidized, and the chlorine is reducing, so it must be reduced. So from this, because the sodium is itself oxidized and it's causing the reduction of the chlorine, the sodium would be the reducing agent, and the chlorine, because it's reduced and causes oxidation in the sodium, the chlorine is the oxidizing agent. You should now have a go at practicing as many of these as you can to identify what's being oxidized, what's being reduced, identify changes in oxidation numbers, and therefore identify reducing agents and oxidizing agents.